calculate the amount of chemicals in a solution. So what is this? Whenever you're trying to compare one chemical to that, and we're talking about solutions, these are chemicals inside of water, we typically want to know some data about it, how concentrated it is, how much of solute you have relative to the solution, which is typically water plus whatever the chemical is. We need that data. So there are different ways to represent that concentration or quantity of solid and solvent, and that's what we're going to talk about. So this section basically deals with these different ideas. So one way you could determine or quantify how much solute you have relative to solvent, and just to be clear, solvent is whatever you're dissolving. So if I have NaCl and I'm adding it into water, I create a solution. Whenever you add a chemical to water, you create a solution, and that solution is going to be the NaCl plus the water. So those two together are called the solution. NaCl by itself is called the solute, whatever you're dissolving, and your solvent for our purposes predominantly is going to be water. Now there are other solvents that can exist out there, but we're going to just focus on water as being our main solvent. A solvent basically represents the chemical you have more of. Whatever you're dissolving into, that's a solvent. So whatever you dissolve is the solute, whatever you dissolve into is the solvent, and when you combine those two, you have what's called a solution. So in the case of mass percent, what we're going to do, we're going to take the grams of the solute divided by the grams of the solute plus the solvent, which is basically grams of solution. So in this example, you have 8 grams of potassium chloride. You can see that in the balance right there. So we put that mass in there first, and we're going to add water until we get to exactly 50 grams. So the 50 grams is your mass of solution. Now, if you're curious and you want to figure out the mass of water, for example, in this scenario, well, your mass of solution is 50 grams. You have 8 grams of solid, so you have 42 grams of water in here. You don't really need that for the calculation, but just so you show you where the numbers are coming from. Because what if I told you you're adding 42 grams of water to 8 grams of solute? You'd say, okay, the total mass is 50. That's what I'm going to divide by. So what you divide by is your total mass. You multiply by 100 because it's a percent question, and you get mass percent. So this tells you how much solute there is in a solution. And this particular example, if we do the number crunching, there's your solute, which is 8 grams. Here's your mass of water, 42, as you saw how I got it. 50 is your total. So to get your mass percent, it's 8 grams divided by 50 grams times 100, so 16%. So 16% of this solution is potassium chloride. What's the rest? Water. So 84% is water, 16% is potassium chloride. That's all the number represents. What percentage of the solution is that chemical? Here's another example of it. You have sodium carbonate, and let's say you have 250 grams of solution. So that means there's 235 grams of water, obviously, right? So in this particular example, to get our mass percent, we're going to take our 15 grams of sodium carbonate, which is here, divide by our total mass, which is 250, times 100, we get 6% of solution. So all you need is the mass of solute and really just the mass of water, because you could add the two together to get your solvent or solution if you wanted to, or the total mass. It depends on what they're giving you. But the only thing you need to remember is the mass of the chemical divided by total mass. Times 100, that's your mass percent. The other variation of this is called parts per million. Same exact calculation. The only difference is you're dealing with a very small quantity of chemical. So rather than have a decimal, like a long decimal, like 0.000064, whatever it is, what we do, we use parts per million as the calculation. When the difference is we're going to multiply by a million instead of 100. Why do you do that? Really, the only reason is because you don't want to see a long decimal. That's really the long and short of it. So in situations where you have a very small amount of chemical rather than the solvent, use parts per million, they'll ask for it. Typically it's water samples. When you're doing analysis of different chemicals inside of water, they represent parts per million because the number becomes a whole number instead of a long decimal, so you have a better grasp of what it is. I mean, that's typically what it's used for. So here's an example of that. Notice 1 times 10 to the negative 6 grams, very, very small number compared to the 100 grams of water you have there, right? So our mass, our parts per million for this is going to be 1 times 10 to the negative 6 divided by that 100 times a million gives you 0.01 parts per million. So we have this. The alternative would be 0.012334, 1. If we did it mass percent, we'd get this. So really the only reason we do this is because this looks a little better than this. That's really the long and short of it. All right, molarity, the other way to determine quantity of solid in a solution is, and this is the more common way because this represents concentration. Whenever you're seeing chemicals, they usually give you the concentration of molarity units. They don't typically do mass percent, so this is the more popular concept. The concept of it requires, or the formula requires, moles of solute divided by liters of solution. Now, liter of solution, you guys can pretty much figure out because just the volume of solution you have, right? But moles is something we have not really talked about. So what is the mole? Well, mole is just basically a unit to compare chemicals against each other, just like a gram, a pound, a liter. Any unit for measurement is used to, allow us to compare two things against each other. So mole is just another one of those. The way it works is that you can't really measure directly. You can't, like volume, you put in a graduate study, you measure it. For mass, you put on a balance, you measure it. For mole, you can't do it directly. So what you have to do is do it indirectly. And what that requires is to use the periodic table. So the periodic table actually has these numbers underneath. Now, you may associate these with the mass of a single atom, and they are. So 1.008 AMU, that's the unit for atom's mass, is equal to basically one atom. So one atom weighs 1.008 AMU. Wonderful. Lithium, same thing. And let's make these whole numbers. So in the interest of simplifying the concept for ourselves, we're going to ignore the decimals altogether. So you're going to round up and down accordingly. So lithium, for example, we're going to call it 7. So 7 AMU is equal to 1 atom of lithium. Okay, so what does that have to do with the mole? So here's what it has to do with it. These numbers are also the amount of grams in 1 mole. So it turns out that 7 grams is equal to 1 mole of lithium. So you're probably looking like, what the heck? How's that even possible? It's really weird, but this is the way it plays out. So without overly complicating it, 1 atom weighs 7 AMUs, right? 7 grams is equal to 1 mole. You want to know how many atoms are in 1 mole? 6 times 10 to the 23rd atoms. Go put all those zeros in and see how big it is. That's a huge number. So when you have a whole crap load of atoms, it's equal to 1 mole, and that is equal to 7 grams. All you need to understand is this. All these masses here are equal to 1 mole. How many grams are in 1 mole of beryllium? 9. How many grams are in 1 mole of nitrogen? 14. Just look at the bottom number. That's all you gotta do. All these are equal to 1 mole. Now, why is that important? Well, remember, you can't measure moles directly. So what if I tell you have 28 grams of nitrogen? And I want to know how many moles it is. So how the heck do you do that? Well, I know that 14 grams equals 1 mole, right? So what we're going to do is use our old friend, the T-chart. So here's our T. Remember, the way a T-chart works, whatever they're giving is upper left-hand corner. Whatever gets rid of that unit, bottom right. And whatever you're looking for unit-wise is on top. So what am I looking for? I'm looking for mole. So I put mole on top. What do I put on the bottom? 14 grams. So doing the math, grams cancel. This is how you know you did the T-chart correctly because the units cancel. You're left with the mole. And the way this works, 28 times 1 divided by 14, which gives us 2 moles. So that's how you figure out moles. You first measure the quantity using a balance, then use the periodic table to get the moles. That's the whole way to deal with moles. And why do we care about that? Because we need moles of solute to get the molarity of the solution. So if I give you the grams of the solute, you can convert it to moles real quick, plug into this formula and get the molarity. That's the end game for us. So here's another example of that. All those mass in the periodic table equal to molar mass. And in case you're wondering, the units for molar mass are grams per mole. That's the units. So going from mass to moles requires a T-chart. So here's another example of it. What if you have 6 grams of carbon? Well, there's 6 grams upper left-hand corner like we usually do. But a T, what do you know we're looking for? Moles. What do you know? Trying to get rid of grams. So grams go away. The only reason we cancel is to verify we set up correctly. So 6 divided by 12 is 0.5. It's basically 6 times 1 divided by 12. So that's how many moles are in 6 grams of carbon. That's how you do the calculation. The other thing you want to be aware of is how do you get molar mass, because you don't always have a single element, right? Sometimes you get compounds. So how do you figure out the molar mass of those? Well, it turns out all you have to do is just add the mass of the elements in the compound. So for H2O, I have 2 H's. So look at, we're going to go 2 times 1 grams per mole. So you have 2 grams per mole coming from the hydrogen. Oxygen, right here, 16. So 1 times 16 grams per mole. That gives me 16 grams per mole. So what's my total mass of the compound? 18 grams per mole. If you want to do another one, let's do CO2 real quick, shall we? Okay, carbon, 12. There's 1 carbon, so 1 times 12 grams per mole equals 12 grams per mole. Oxygen, there's 2 of them, times 16 grams per mole, gives me 32 grams per mole. So what's the molar mass of CO2? 44 grams per mole. So all you have to do is just keep an eye on the subscripts, because you multiply that times the mass you see in the periodic table to give you the molar mass of that element. So let's try some of these to make sure you understand it. Calcium carbonate. Okay, where's calcium? Right here in the bottom. Carbon is right here, and oxygen's right there. So basically we have 12 for the carbon, 40 for the calcium right there, plus 48 for the oxygen. For those wondering how I get 48, 16 times 3, that's how you get 48. So your molar mass of calcium carbonate is 100 grams per mole. This is a little tougher. Ammonium phosphate, that's a lot going on for it. So nitrogen's 14, hydrogen is 4, so that's 18, and then we have to multiply that 18 times 3 because we want to get the mass of the whole thing. That's 54. So you have to distribute the 3 on the outside to everything. You could also do 3 nitrogens, 12 hydrogens, and do that math that way. That's fine. Or you could combine them together and multiply them by the number outside. It's really up to whatever your preference is. Then you add 1 phosphorus, which is 31. And then you have oxygen, 16, and you have 4 of them, so that's 64. So you add all that together, you get your molar mass. So 14 times 3. Why 14 times 3? Because you have 14, and you have 3 nitrogens. Remember, you distributed 3. Plus 1 times 12, because there's 12 hydrogens. Each of them is 1. Plus 31 for the phosphorus, plus 64 for the oxygen. You get 149 grams per mole. So it's up to you whether you want to do the parentheses, distribute before or after. It's really a preference thing. Calcium chloride, calcium's 40. Chlorine, chlorine's a weird one. So everything else you round up and round down. You may want to keep chlorine as 35.5, but if you do 36, not the end of the world. It's really a preference thing. You can see here I did it as 36 times 2, so I rounded it to 36. But if you did 35.5, you're fine as well. Just don't do 35. That's bad. So 40 plus 72, 112 grams per mole. Another tough one, 2 times 56, because that's where iron is, right there. So I rounded up. So together or apart, really up to you. You could do 32 plus 64, which is equal to 96, and multiply that times 3, or 3 sulfurs and 12 oxygens. Really up to you, whichever way you work. You can see I do it on the examples or worked out example. I did 32 times 3, so I distributed, and then 16 times 12. But it's really, it doesn't matter, whatever you're more comfortable with. All right, so why did we do all that? We did all that because now we understand how to get molar mass, which means now we can get moles from grams. So I have 25 grams of magnesium chloride, and you're trying to make a 450 milliliter solution. So they're looking for molarity. So the first thing in your mind when you say the molarity, just write the formula down. Moles over volume. And then just forget the number. So how do I get moles? Well, for magnesium chloride, I do 25 divided by 95.21. You could just make it 95. You don't have to worry about the decimal. As long as you're in a zip code of the correct answer, you're fine. I'm not going to deduct you for it. So 25 divided by 95 is equal to 0.263 moles of magnesium chloride. That's not molarity, that's just the moles part. So how do I get the molarity part? I need to go divided by the volume. But the volume has to be in liters. This is milliliters. So how do we go to liters from milliliters? Really easy. Decimal point, if you don't see it, it's always at the end, right? So it's right here. So we're going to move it over 3 times. 1, 2, 3. So you get 0.450 liters. That's how you go from milliliters to liters. Decimal 3 times to the left. We're going to do that, then divide, we get 0.584 molar. That's how I get the molarity of the solution. Pretty small number, right? Less than 1. So is this a concentrated solution? No, it's pretty watered down, if anything. All right, common use of molarity, really it's to either have a specific amount of concentration you need for that lab, right? You need 1 molar, 2 molar, whatever the lab requires. That's one possibility. Other, you're trying to make a chemical less dangerous for yourself. When you get acids and bases from chemical supply companies, they make it at 14 molar. If you put 14 molar sulfuric acid in your skin and everything underneath it, including your arm, will be gone. That's how strong sulfuric acid is, 14 molar. But if I make it at 0.5 molar, still not super safe, but not going to do as much damage either because it's more watered down. So that's the whole point of trying to figure out how to make something more watered down, more dilute. Is because you want it to be less dangerous for yourself. You don't want it to kill you because you're doing an experiment. That'd be crazy. So how do you make it? So you typically use a volumetric flask, and the way it works is this. You measure at the mass you need for that molarity. So if I want 1 molar, which is what this particular situation requires, so 1 molar means I need basically 58.5 grams of NaCl, which is what 1 mole is equal to for NaCl. You could divide it by the molar mass and you'll verify, per 1 liter of solution. Now, this thing measures to 1 liter. This line is 1 liter. As soon as I put enough water to get to that line, I have exactly 1 liter solution. Now, why do I emphasize this? Here's why. You add your solid, so 58.5 in this situation gets dropped in there. Now half fill it. Why don't I just fill it to the line? Because you don't want the solid to dissolve and make the water level go above the line. Whenever a solid dissolves, it's going to take up space. That's just a fact of life. So if you were the superstar that filled it to the line, after this thing dissolves, it's going to be above the line. You just screwed up. Your solution is not going to be what you expect it to be. Done deal. So how do you avoid that? Half fill it with water, dissolve it all, and then fill it to the line. That's how you avoid it. So that's how you make a solution in a volumetric flask. Half fill, dissolve, and then fill it to the line to make whatever volume you're shooting for. So notice once again, add the solid, half fill with water, dissolve, and go from there. All right, what's the molarity of a solution of 225 milliliters of 225 milliliters contains 34.8 grams. So they're asking for molarity. So all I need to do, just write this. Don't worry about the wording. Don't let it throw you off. I'm going to change this to liters. 1, 2, 3, 0.225 liters. I'm going to change this to moles by dividing it by the molar mass. So 34.8 divided by 101, or if you really want to go decimals, go for it. So you get 0.344 moles of potassium nitrate. Cool. I got the moles part. Yay. Now I need the volume. So what's the volume going to be? 0.225. Plug and chug. There's your molarity. That's all you got to do. Go to moles, divide by the volume. Have a nice day. All right, so speaking of dilution, done to lower the concentration of a solution by adding more water. And like I said, it's to make things less dangerous. That's the long and short of it. How can you tell something's dilute? It's a lot lighter. Look at this red. Look at this much lighter red. That's what dilution is. You've all experienced it. If you've ever had soda that you had the ice melt before you drank it all, you notice the flavor is different. Why? It's watered down. That's what dilute means. Dilution is basically watering something down. It's a fancy way of saying watered down. So if someone wants to dilute your soda, they're basically just watering it down. You could tell dilution level based on color. So you can see this is going from light to dark. So which one is the most concentrated? Assuming these are all the same chemical, different quantities, you could tell the one to the right is the most concentrated, right? And the one first to the left is least concentrated. Like you would not drink the soda on the left if this was soda. You drink the one on the right because you want flavor. The formula to deal with dilution is M1V1 equals M2V2. This is the concentration when it's diluted, watered down. It's the original. So here's an example. So the way it works, the M1 and V1 are going to be given to you. There are scenarios where they're not. They're looking for either the M1 or V1, but we're not going to worry about that right now. We're just going to go with the watered down version. How do you figure out when it's watered down, what the concentration is of the new solution? So this is your V1, this is your M1. This is your V2. So we're looking for M2. So we're going to rearrange this equation just like algebra, and we're going to divide by V2. So whatever we're looking for, we take the other thing, stick it underneath, and divide by it. So here's our setup. M2 equals M1 V1 over V2. Plug and chug, you get 0.2 molar. This is the watered down version of the solution. So when you make this particular variation, that will be the concentration. Let's try another one. This one's a little tougher. You have 3 liters of 3 molar NaOH with 3 liters of NaCl. This is more typical conceptually because it requires a little bit of thinking. You know this is your V1. You know this is your M1. Here's the problem. Is 3 liters your V2? Well, if that's your V2, then what the heck are you doing? It's the same thing, right? Your V1 and V2 are the same. They can't be. It's impossible. So what happened? You have to think. You had 3 liters, and then you decide to add 3 liters. So guess what? You have a total of 6 liters. That's your V2. So a question like this, you have to use some reasoning skills and ask yourself, well, if I'm adding the two together, does it mean the volume is going to be the total of 2? Yeah, absolutely. That's exactly what it is. So that's how we're going to set it up. 3 liters times 3 molar divided by 6 equals 1.5 molar. And you're done. That's all you had to do. The trickiest part is figuring out what the V2 was. All right, here's another example of it. We have KOH when you have 15 milliliters, 2 molar. KOH is mixed with 45 milliliters. So this is bigger than this. So some of you guys may look and say, oh, okay, your V2 is 45. When you're mixing two chemicals together, guys, the total volume is going to be the combination of those two. Always. You're mixing two different volumes together. Of course, the total volume is going to be, you add the atom together. So that's the only brain fart I see this kind of question. People forget to add those two. They just use 45 because they're not thinking. You're mixing two chemicals, guys. Add. Remember that. So here's our formula. Generic, nothing changes. You can pretty much just memorize this. M2 equals M1 V1 over V2, and that's how you just handle it. So plug and chug. 2 times 15. Notice 60. Where did it come from? 15 plus 45. That's where it came from. So we had a 0.5 molar solution. That's how you deal with concentration of solutions and the different calculations.